All right, so the title of my talk is Reconstructing Large-Scale 3D Models from Images. I thought I'll say a few words about my background. As I mentioned here, I did my PhD in mathematics in 2001 in Lund. Then I went abroad for a couple of years. I was 1 year at the Australian National University, followed by 1 year at University of California in San Diego. Then I came back to Lund again, continued doing research on these topics, and as of recently, 2 years ago, I moved to Chalmers, so I now have a joint position at Chalmers and Lund. So I've started a new computer vision group here at Chalmers, and we're starting to become a handful of people doing research on sort of both what I'm going to talk about today, 3D geometry and applications thereof, and also medical image analysis, which I won't talk about today. All right, so my research field, computer vision, can roughly be divided into 3 research areas, which are very interconnected. The first one is recognition, sort of saying what objects are present in an image. The second topic is reconstruction. Imagine you go around in a city, you take a bunch of photos, and sort of what can you do with those photos? Here's a 3D reconstruction. So this will be my focus in this talk. Another research area is segmentation, which is the problem of partitioning an image into meaningful segments. In this case, it's an MR image that's been segmented into different compartments of the heart, so you see the right ventricle and left ventricle, etc. All right, so the brief outline of my talk, I'll start with some introduction, and then we'll go over to the main topic, 3D reconstruction from a collection of images. So I won't use so much dynamics here, so they are not needed to be taken in a sequence or anything like that. And we'll see several applications and also generalizations of sort of basic setting. And finally, I'll conclude. All right, so when I go to a dinner party or something like that, and people ask me, what do I do? Then I often make this analogy with computer graphics and visualization, because everyone knows what that is. You have some sort of scene model or model of the world, and you want to produce nice images. Okay. But what I'm interested is in the inverse problem of computer graphics. So I have my images, and I want to draw conclusions about the world, the 3D world out there. So, of course, since it's an inverse problem, it's much harder, of course, right? So I thought I'll start with some historical remarks on this topic. I think one of the starting points was a paper by Longitudes in Nature in 1981, where he showed that it's actually possible with quite a simple algorithm to reconstruct the 3D geometry from 2 views. So that started a whole lot of things, in particular in the 90s. I think it was the sort of golden era of projective geometry. I know Kahl was a lot involved in that, and that was my starting point as a PhD student as well. We sort of we're interested in what is possible to do with cameras and what is not possible to do, and how do you model cameras in a nice mathematical framework, and that was projective geometry. And this is nicely summarized by the Hartley-Sisman book, which is still considered the Bible in this field. All right. After that, I think people concentrated more on computations. How do you do efficient computations? And how do you involve more images? So here's an example of what I did 10 years ago. You sort of have a input image sequence of 36 images, and it's a turntable sequence. And this is just a toy example, of course. It's a toy dinosaur. And what you could get out of this automatically was how the camera has moved and the viewing direction of the camera. You see the camera trajectory. We know it should be a circle, since this was taken on a turntable sequence. And here you got some sort of 3D point cloud model of the toy dinosaur. And from that, you can work out what is a nice surface model out of that as well. All right, so that's sort of what we could do 10 years ago. And this was further pushed by speeding up the methods and the the basic methodology. I think one nice paper was by Samir Agarwal and colleagues, where they show that you can sort of build Rome in a day using many, many images. So I'll come back to that, give examples of that later on. But one idea that they used, well, you have to have a lot of images, so maybe you don't want to take them yourself. So then the internet is, of course, a good source of getting images. So if you go to Flickr, for example, and you type in a keyword like Rome or something like that, you can download basically millions of images taken in the city of Rome. So that's a very good source. So that's what we and other research groups been using for creating very large-scale 3D models. All right. So we have this technology now, and what has happened in the last couple of years? I think one thing that has happened is that there's been a massive interest from industry in this technology, in this field. So, I mean, there are tons of startups using this technology. The automotive industry has been a driving force as well. I mean, they have realized now you want to build 3D maps of the world. So, and major internet companies like Google, Microsoft, they have whole divisions of computer vision researchers. So it's a whole different thing of going to computer vision conference today than compared to 10 years ago. So I think that's a very interesting development. All right, so what's the sort of, how do you do this? Well, here's a sort of example of the reconstruction pipeline. So you have your images, and I've already, maybe you noticed that Kahl have used same images, but I think that's fine. These are from Örebro Castle. So we have extracted a bunch of interest points here in red. So they're sort of corner points where there are lots of things happening in these images. So suppose we have 4 of them. So what you do in the first step is you try to find similar points in the other images. So you try to match all the points here to all the points here by looking at texture and such things. So you try to do this automatically, of course. You'll end up with lots of mismatches. So you have to be, that's one of the challenges when you going to apply this technology, that you have to be able to handle all these outliers. And then you do that sort of for all pairs of images where you can find correspondences. And once you have that, you have something to start working with. Then you're sort of down to points, and then you can sort of set up an optimization problem and try to solve this optimization problem, and you can end up with reconstruction like this. So here's a 3D point reconstruction of Örebro Castle, and here is where the cameras were taking the images. So this is some 800 images of Örebro Castle. And this is, you just feed in the sort of images into the computer, and what you get out in the first step is this. And further, this can of course be enhanced. You want to reconstruct the surfaces out there as well. So you, in a second step, we do that. And this is sort of a typical example here. What kind of surfaces you can get out. So this is, we have done no post-processing here. You see sort of spurious pieces here as well, which you could remove if you want to clean it up, if you like. But yeah, so this is done fully automatically. No tuning or sort of no manual intervention here at all. All right. I'll show you some more 3D rigs on the Cathedral of Lund. So this is taking, it's around, well, almost 1,000 images that we fed into the computer, and now you can sort of navigate around this, and you can sort of visit the different images, and you see, when you see the image and it's consistent with the 3D model, then you know you have done correct reconstruction. That's a good way to validate your algorithm. So I'll give one more example here of even bigger one. Let's see if this one can start. So this is based on even more images. It's the old city of Dubrovnik, and these are internet photos just downloaded from the internet with the keyword Dubrovnik. And you see where all the people, I mean, these are taken by different cameras, and you can sort of go around and see where people have taken images over the city. And the sort of model here consists of a couple of million of 3D points. So it's quite a big model, I would say. All right, so let me say a few words about application. I mean, when I started doing this, we didn't know of all the possible applications out there. They have come up after when you sort of realize the technology. But I think they can sort of be categorized into two different subsets. One is when you're interested in the 3D geometry of the scene model itself. So we have seen, I mean, object models or visualization of architectural or archaeological sites is an important application. We're also using this for construction of 3D maps. The other application area is when you're more interested in the camera motion. That's what Fredrik talked about earlier. If you want to use it for navigation of an autonomous system, for example, you put it on a quadrocopter, a camera on a quadrocopter, then you're more interested in estimating your ego motion relative to the world and make sure you don't crash into things. I'll show you some example that we have done on localization as well. I've shown here two examples which have led to startups that I've been involved in. One was Polar Rose, where we constructed a system that took 2D images and constructed 3D face models. And this was from a single image. So we sort of had priors on how faces look like. Another more recent was this idea that, well, if you can scan or make a 3D model of yourself, you can also print it. So I haven't printed myself, but this is a company doing this in Germany now. So here's another example. So basically you sit on a chair and you turn it around, so you get this bunch of images. So you can sort of build up a 3D model of the person sitting on the chair, and you can see the camera positions. Again, they should be in a circle, right? This is a special case again. And so this you can download and test at home if you like. You can also send, if you don't have a 3D printer at home, you can order a 3D copy of yourself here, right? All right. So another application area which we've been working on is image-based localization. So suppose you have a 3D model of a city. This is a 3D point representation of Malmö, or a big part of Malmö at least. So we've been looking at the problem. Given you take an image and you want to say where was this taken. So we're not using any GPS information or anything at all. Just purely based on the image, we can say where this image was located. And it works quite well. There have been some big steps in sort of realizing this technology. So I think it works quite well. Of course, I mean, if the image, I mean, that's sort of, if you only see the sky, you can't say where it was taken. So I think this is a nice example of showing the potential, what you can do with only using a camera. All right, so let's see. I thought I'll show you some other applications, or what we're currently doing. We're interested in problems where the scene you're viewing is not necessarily static. So, for example, things might be deforming, or there are dynamics objects in the scene that we want to reconstruct. So I thought I'll show you some work in progress on that. Yes. So here's a sequence from Iron Man. Here on the top left, you see the actual original sequence. And here on top right, you can see all the points we have tracked throughout the sequence. And here on lower left and lower right, you see actual 3D reconstructions of these two sequences from two different perspectives. So that was just a sort of teaser of what we'll soon be able to do let's see. Sorry, I was almost going to finish there. All right. So we have also used this, similar to what we heard earlier, putting a camera on a quadricopter and mapping interior indoor environments. We have used it for. A lot of people involved in this, people at Chalmers and people at Lund, and also some external collaborators. So I think I'll conclude there, but saying that I've presented computer vision now from a purely geometric viewpoint. I hope I've convinced you that it's possible to do large-scale 3D models automatically from images. And there are lots of interesting applications, I think. Visualization, localization, mapping, self-driving cars, etc. And I'm sure there are plenty more to come that we haven't realized yet. So thank you very much.
Thank you, Fredrik. So give me 2 areas of usage. One that is where you can see already now where this can make a big impact, and also an area that we don't really think of, that you think this can have an impact on.
All right.
Någon som är liksom, det här är självklart användningsområde, och något som är inte lika självklart, men du tror att det kommer få en
So
effekt.
I think construction of 3D maps is one big area. I mean, we can already now go to Apple Maps and get nice 3D reconstructions. And it's basically based on this technology, because there are people that Kahl and I have supervised that are working with Apple just doing that, for example. So I think that's, yeah, I mean, these 3D maps are interesting for the car industry as well, for driving. They need 3D maps, good 3D maps of the whole sort of all the roads and all the cities in the world to be able to. So I mean, that's coming soon. Yes.
Okay.
So an area that what was your second question? An area, upcoming area?
Självklart, ja precis. Det är inte lika självklart, men ändå, där du ändå kan se att det här kommer få ett genomslag.
Well, it's really hard to say. I mean, I think when the Kinect camera came a couple of years ago from Microsoft, it has a 3D sensor, and then suddenly lots of people were suddenly interested in 3D. But I think we don't need the Kinect always. We can get away with, I mean, doing it with standard cameras. So all the things you can do with Kinect, I would say you can do with standard camera. So I mean, so it's really hard to predict what's going to happen.
Are we going to have 3D machines in every home in a few years, you think?
3D machines.
It's like asking 30 years ago about the computer. Is everyone going to have a computer at home? No, it's too big, it's too expensive, it's not possible. But now everyone is having computers in homes or in our phones. Is it the same thing with the 3D scanner, you think?
Well, I mean, you already have that today with your computer in a way. It's just...
yeah, but I mean, actually building the product in 3D, like we saw the
I think, I mean, we already see here today lots of companies using 3D technology. So,
but do you think we're gonna, as a private person, gonna have it at home? Oh damn! I need a screwdriver, so I load it down from internet, and we make a screwdriver.
Well, I mean, that's the 3D printing story. I mean, maybe we'll have that. I don't know. I mean.
Okay.
Yeah, I'm sort of the basic scientist coming up with the possibility of doing it, and then I'm letting everyone else to use the technology. Sort of. But
okay. So any questions for Fredrik? And we have also in the back row.
Thank you. Yes, a question about the algorithms used to recreate the geometry. There are a lot of several companies selling commercial products for photogrammetric modeling.
Sure, yes.
They all seem to have the same problems, like shiny surfaces and transparent surfaces are causing problems.
Mm-hmm.
Are you all using the same algorithms, or do you have different solutions?
Are we all using the same? Well, there are good algorithms and not so good algorithms, so they are not all using the same. But I mean, there are difficult scenes where you have lots of specularities and dynamics and yeah. So there are really challenging scenes, which is so we're not able to reconstruct 100%.
Is there a research done right now to like address these shortcomings?
Yes. I mean there are a lot of research groups trying to push the limits of what's possible, and I mean we are one of the groups trying to push what scenes are possible to reconstruct, and how can you sort of make it more efficient, be able to prevent it from failure, because that's a big difference now compared to 10 years ago. We're able to reconstruct many more scenes, but that's because we have much more robust algorithms now than we had 10 years ago, I would say. So it's improving all the time, and it's a very competitive field. There are lots of interesting, there are lots of research groups interested in this problem all over the world, so they are sort of competing on getting the best algorithm. So.
I also have an idea I want to pitch about the applications of these. Like if you have a scan of an entire city. I was experimenting with augmented reality a while ago, and the problem is usually if you don't have feature tracking, solely relying on GPS is not good enough to get the accurate projections of the generated images.
Yeah.
Could you use this data set you have from the scans to actually use them as feature trackers for the augmented reality? So if you walk around in the streets and you hold your smartphone, you could actually use this data as feature trackers to like.
Oh yes, I mean there are systems that do exactly that. But then there's the problem of sort of having an updated model of the 3D world, of course.
That's where the drones come in.
Yes, sure. But
okay.
That's perfectly.
Are there commercial products, or is it just?
I don't know so much about the commercial systems out there for that. But, yeah.
Okay, thank you.
Yeah.
Det var där bak, Åsa, till vänster. Vinka en gång till. Wave again. So I was thinking the environment and cities, they change. New buildings, etc., etc. Can you keep this updated so that you have the latest view?
Yeah, well, that's a challenge. I mean, both for the sort of car manufacturers that want to use this for having cars driving around on the roads, but I think there's a new spin-off in Malmö, which is called Mapillary, which use crowdsourced images. Okay. So there are several thousands of people contributing images every day, and they update it constantly. So maybe that's a good way. And when we'll have all these autonomous cars driving around taking photos, I mean, that's also a way to update our model. I mean, so I think that's a possibility of keeping the 3D model of the world up to date in a way. So I think that will happen.
Yeah. So I have a question about smaller scale 3D models with more detail, and perhaps taking pictures of like more technical things that requires a more detailed level. Of course, that has to do with like 3D printers and stuff as well. But when we saw the 3D recognition of the face, it's not like super detailed. Will it get more detail, and will it get there soon, or yeah?
Yeah, I mean that's also an area that interests us, of getting very sort of fine detailed reconstructions. So I mean, we're sort of pushing the limit in that direction as well. When you have maybe lots of photos and very complicated, thin, elongated structures, that's very hard to reconstruct actually. So, I mean, I mean, we're working towards that goal of getting very fine, detailed models as well.
Final, the last question, when are we going to see a 3D model of the world?
Well, yeah, that's a good question. I mean, we have, like I said, Apple Maps. They have something of the major cities, and maybe Mapillary in Malmö will contribute to that if everyone is sort of taking images of the whole world. And I mean, yeah, we're soon there, I think.
Okay, cool.
Getting a.
Thank you, Fredrik.
Yeah, thank you.